Friday, okay? And that timing will work out really well, accidentally, because most of you guys I will not see for all of next week because you will be at business week, okay? So we'll go ahead and finish this chapter up. We will review for the next couple days and then have the test Friday, yeah. I'm not going to make any plans on that. We do have school on Friday. What's that? No, this Friday, this week is a normal week. Okay? Zoe, shh, shh, shh. Zoe is hoping and anticipating and getting excited about having a snow day. I'm not going to make plans based on that. Okay? Yeah, I'm sure you are. All right, so here we go. Let's wrap this up. Today, we're going to do transformations of polynomial functions. It is the easiest topic ever because we have done this again and again and again and again with other functions. And all of those rules apply to polynomials as well. So here's what it's all about. You know this already. You do. If you take a function and multiply it by a number, what do you get? What happens to the graph? If you take a function and multiply it by a number, what happens to the graph? In what way? This is transformations of polynomials. It could be a shrink or, Colby, or a stretch. Okay? So if you multiply by a number, you get a shrink or a stretch. Okay? If you add or subtract a number inside the parentheses, what does that do to the graph? Side to side. Good. That's what I said. Okay, if you add or subtract a number to a function outside the parentheses, then it moves it up or down. Transformations. Transformations. If you multiply by a negative on the outside, that will take the graph and flip it over the x-axis. If you multiply by a negative inside, that will flip it over the y-axis. Okay? So those are the different transformations. Those are your basic transformations. Like I said, we've done this a number of times with different kinds of functions. So you should be relatively familiar with these rules already. Yeah. Outside the parentheses or inside the parentheses? Kind of, yeah. Are you ready for an example to make more sense? Okay. You good? Okay. Oh. What? Just, I guess, to show that these same rules apply to these types of functions as well. Right. But this is the end of the chapter. This is like kind of the wrap up. This isn't like we're starting a new thing. Yeah. Yeah, right. Okay. Okay, Ashlyn. Sydney compressed the factor by 1/2. Now we want to reflect it across the x-axis. A vertical compression shrinks the graph. So, for example, if I start with y equals x cubed, that graph looks like this. Okay, I'm going to zoom in a little bit so we can see a little better what's going on, because this is kind of a strange one. If I now make this 1/2 x cubed, then can you see that, see how the blue graph is closer to the x-axis than the red graph? It's like the red graph has been shrunk down a little bit. It's been sat on. So, okay, so that's what a vertical compression is. If I took this decimal away and made it a 5 instead, then that would be a stretch of 5. So now the blue graph is farther away from the x-axis. It's been stretched instead of shrunk. Okay, does that make sense? Okay, so your job now is to take this blue graph and flip it over the x-axis. How do you do that? I'm Ashlyn. Yep, want to flip it over the x-axis. Okay, good. So that means I'm going to change this to y equals negative 1/2 x cubed. And that negative is going to take it and flip it over the x-axis. Okay? So if I put a negative in front there, see how that turns it over like that? Okay. Some of you were a little bit confused about the inside-outside that I said. They were like, inside or outside of what? So outside of the whole function, that flips it over the x-axis. If I wanted to flip this over the y-axis instead, then I would need to put the x in parentheses, put a negative in front of it right there inside the parentheses. And then that would flip it over the y-axis. Okay? It is the same thing. Good. In this case, it's the same. It's not always going to be the same, but in this case, it works out to be the same because, man, I would give you guys $1 million if I could, if you could answer this question. The reason why it comes out to be the same in this case is because y equals x cubed is an odd function. And so anytime you have an odd function, if you flip it over the x or flip it over the y, you end up with the same thing in the end. Okay? Callista? Right. Uh-huh. So, okay, well, let's do the next thing, shall we? Okay, so the next thing then is we want to move it 3 units to the right. Okay, so let's see how we can do that. Ariel is not here. Alexandria, how can I take that graph and move it 3 units to the right? Good, excellent, because inside parentheses, I don't know if you guys remember this or not, but inside the parentheses is always the opposite. So if I want to move it 3 to the right, I actually have to go x minus 3 inside the parentheses. So let's do that on our graph. So if I put a minus 3 in there, now you can see the graph got moved 3 to the right. Okay? All right, and then the last one. Brennan, now I need to move it up 2. Good, plus 2 at the very end. So y equals negative 1/2 parentheses x minus 3 cubed plus 2. Okay, there's the 4 things that give us these 4 transformations. Okay, yeah. If I go plus 2, that moves it up 2. All right? because it took this and then flipped it. So this piece right here is facing down like that. So if I get rid of this negative, then it looks like the same graph just moved around. But if I put that negative back, see that's flipping it over the thing. Yeah. All right, you guys feel relatively okay about those transformations? Yeah? Okay. No, you could just write your final answer. I was showing the steps because I'm a teacher.
Look at how good I took notes. I took from there to there,
Mm-hmm.
and I put like all of these, so I know.
A plus. Okay. Yes. All right. Let's do a little bit of algebra with one of these. It says, what are all the real zeros of this function? And so if you're trying to find the zeros of the function, the reason they're called the zeros of the function is because you find them by setting it equal to 0. All right? So what do I do first? Good. So I subtract 6 from both sides. So that's negative 6. Yep. And then I divide by 3. Okay. So this is x minus 1 cubed equals negative 2. Okay. You guys are going too slow. You guys need to focus up on what's happening here. You're spending too much time chit-chatting and then you get behind. Okay. Let's go. Let's go. Pick up the pace. Okay. Shh. What's that? I did subtract 6 from the other side. I went minus 6 right here and minus 6 right here. Those canceled. Okay? Okay. All right. How do I get rid of the cubed? I not square root it. I cube root it. Okay? I cube root both sides. So the cube root and the cube cancel each other out. Yep, that is not very pretty. I do want to talk to you just briefly about the cube root of negative 2, okay? Two things. One is, I've told you guys before, and it's not a lie, that you can't take the square root of a negative number, okay? You can, however, yeah, you can have imaginary answers, but as far as this problem is concerned, we're looking for the real zeros, so we're not going to mess with imaginary numbers. Hang on just a second, please, Peyton. The cube root of a negative number does exist because if you take a negative number and multiply it by itself 3 times, a negative times a negative times a negative is a negative, okay? So that's your first side note, that you can take odd roots of negative numbers. The other thing I want to make sure you understand is that when we take square roots when we're solving equations, you get a plus and a minus. That's not the case when you're taking cube roots. You either get a positive answer or you get a negative answer, not both, okay? A 3. It's a 3. Okay, what do I need to do now to get rid of the negative 1? Yeah. Right, just do the positive one. Instead of an x, you mean? Oh, you mean any number right here? Okay, how do I get rid of the minus 1? Add 1 to both sides. So that gives me 1 plus the cube root of negative 2 is my only real solution to this problem, okay? How many solutions will this problem have? 3. What are the other 2 answers? What's true about them? Nope, not that would be a real solution also. We don't know what they are, but what's true about them? They're imaginary, okay? They're imaginary. And so this one, this question is specifically saying just the real zeros. So we got this answer, so we're just going to call it good with just having 1. Yeah. Well, if you're going to do that, you'd have to do the exponent first. So you'd have to figure out what x minus 1 cubed is first. You could use the binomial theorem, Pascal's triangle, to do that pretty quickly. But Yep, that's absolutely right. Okay, one thing that is true about cubics that you probably won't find super interesting, but I'll bore you with it anyway, is that if I start with this x cubed thingy, I'm just going to do it with the most general coefficients, what we were doing in the beginning for our transformations. If I start with x cubed, because x cubed only crosses the x-axis once, it doesn't matter what other numbers I use for a and h and k, that graph will always only cross the x-axis once as well, okay? So if the original function only has one real zero, if you use transformations from there, then you're never going to get more than 1 0 out of that, okay? So it just, I mean, just no matter what those numbers are, there's only going to be one real solution, okay? The way that you get more than one, like these right here, if you want real solutions, is you have to put in like an x squared and an x in there, and then that will change the graph. What's that? We will, yeah. I mean, we have been. We've been solving okay, next one. What is a quartic function with only two real zeros, x equals 5 and x equals 9? Quartic means what degree? Fourth degree. Okay, so if you know that these two things are the zeros, what can you put in parentheses? Good. X minus 5 and x minus 9. But if I FOILed that out, what would I get? What degree polynomial would I get? Only 2. I'd only get a quad. You're close, Amy. But if I put an x squared here, then that changes this 0 from being 5 to being the square root of 5. Okay? So how can I put a squared in there to make this into a quartic? What's that? The outside. Good. If I go like this and like this, okay, now if I FOIL that stuff out, I will get an x to the 4th. Okay? But because I put the squared on the outside, what's that? It's still going to have zeros at 5 and 9, because if I write this out, she said to square the outside, so that means basically what she has created is this. And so what makes these two things equal 0? Still 5. So my zeros are still 5 and 9. What's different about them now that we've talked about before in this class? What did Zoe change by making them squared? Good, the multiplicity. So these both now have a multiplicity of 2, which is what makes this into a quartic instead of just a cubic. Okay? So that works. Okay, tell me when.
If you get a problem like that,
Uh-huh.
it says like x minus 3 and x minus 4, you can just get it like that. Like every time you
Yep.
do
Yep. Super easy. Yeah.
answer.
That's just the answer. Okay. Can anybody think of another answer that'll work?
0.
Can anybody think of another answer that has 5 and 9 as the zeros and is going to be a quartic? Can anybody think of a way that we can change this to make that work? No? Okay. If you take this and make it just one of them cubed, then you would still end up with a quartic. Yeah, so you're on the right track. As long as the exponents add up to 4, then you're going to get a quartic equation. Okay? All right? All right, so last thing, let's finish with a little word problem. Let's say at this particular wind farm, I think it said 30, but that, yeah, 30. What's that? Okay. At this particular wind farm, the power generated by the wind varies directly as the cube of the speed. Okay, let me show you what that means in math. Okay, hang on. The power varies directly as the cube of the speed. Does that make sense? Here's the power. Varies directly means there's some number we're multiplying it by, and then this is and then I cube the speed. Okay? Yes. It could be, yeah. So in this problem, we're given some initial information that when the wind is 80 meters per second, or sorry, 8 meters per second, you get 600 kilowatts of power. So they would like for us to take that and figure out how much power we're going to get if the wind is 10 meters per second. All right? So here we go. I'm going to plug in 8 for the wind velocity, and that is going to give me 600 as an answer. All right? Anybody know what 8 cubed is? 8 squared is 64. 8 cubed, oh, sorry, forgot. Thank you, 512. Okay, so that means that in this case, 600 equals k times 512. So now we can use that to figure out what that multiplier is. How do I figure out what k is? What's the 5? Divide. Yeah, because it's k times 512. So I'm going to divide both sides by 512. And when I do that, I figure out that k equals about 1.17. Okay? Because I remembered from first period. All right? I'm not like a savant or something. So what that means is for this particular turbine, I'm sure it's different depending on how they're constructed. Whoops. The power that you are going to generate is 1.17 times the velocity of the wind cubed. Okay? Right. So now if the wind speed picks up to 10, 10 cubed is 1,000. And so that means I just need to move the decimal over there, right, 3 places. So yeah, 1,170 kilowatts, okay? So in this case, since the amount of power generated is based on the cube of the wind, if the wind speed just picks up a little bit, 2 meters per second, the power that you generate almost doubles, okay? Isn't that interesting? What?